Hello, this is Jack Wild. This is my submission for community problem number 2. So far, chapter 2 seems to be focused mostly on shortcuts for calculating the derivative. And thank God, am I right? Community problem 2 is split into 2 parts, and for each part there are 2 or 3 rules that let you solve the problem pretty quickly, some shortcuts if you will. So I'll just take a second to review them. Part 1, sum and constant rules are going to be what kicks in the most on this. So we'll start with the sum rule. I copied that right out of the book, and if you say it out loud, your head explodes. But what it means is that you can break apart a function whenever you see plus and minus signs. You break the function up into its constituent terms. So this f of x equal to y plus z, you can actually deal with y and z separately. So you can solve them, or maybe you can find their derivatives, and then you can just add them back together, and that gives you the derivative of the original function. So that's pretty great. The next rule that's going to play a key role in answering the questions for part 1 is the constant multiple rule. This rule says that you can also break apart the terms in a function whenever you've got multiplication or division. So then you solve the smaller piece and then recombine them. So the 6y plus 3z, you can actually deal with the y and the z separately and then just multiply the results. And if you combine them again, then you've got the derivative of f. So these 2 rules act together to turn into sort of like a reverse order of operations. And it lets you break down complicated problems into smaller bits, which I find is the key to problem solving both in calculus and life in general. So let's go ahead and apply this. First up, there's a setup for questions in part 1. We're given 2 functions, except that we're not given the formula for the functions, just the output and the derivative when you input 2. So for the first function, f of x, the value is 5, and the derivative is negative 1/2. For the second function, g of x, the output is 3, and the derivative is 2. So I don't know why I feel compelled to graph things, but I had the time, so here are the points and the tangent line of the derivative for both of these functions. Why not? Okay, so the first question asks us to take a new function that is defined as the sum of our 2 little functions. I know that we're subtracting the g function, but I'm describing it as summing because addition and subtraction are inverse operations. And I'm trying to tie this back to the rules we just looked at, specifically the sum rule, which tells us that we can find the derivative of this function by just summing the derivatives of the components. The constant multiple rule also comes into play on this one because the component functions are multiplied by constants. I'm getting ahead of myself. Let's start by finding the value of h2. So h2 is going to be equal to 3f of 2 minus 4g of 2. Since we know what those values are already, they're given to us, we can just substitute those in, and math, and more math and math, and then we find out that h of 2 is equal to 27. So just put that on the graph as well. And see what's next. Then let's find the derivative. Again, thanks to the sum and the constant multiple rule, we can just substitute the derivatives, which we already know. We multiply them by the constants and solve. And then, of course, I'm going to put that on the graph as well. Haha! And if we wanted to turn that line into an equation or calculate the equation of that line, which is actually what part B is instructing us to do, then we'll go ahead and just use the old equation formula here. I botched this one pretty bad on community problem 1, so I'm trying to do it correctly this time. I think I've checked my work a couple of times. So thank you everybody else in the class who did this before me. Yeah, so again, just plugging in our numbers there. Our y value is 27 when our x value is 2. And we throw in the slope, which is equal to the tangent, excuse me, the derivative. And then just, math. And there's your equation. Y equals negative 19/2 of x plus 46. And a new function, and then asks us whether it's increasing, decreasing, or neither at 2. Another way of asking this question is, what is the rate of change of the output when the input is 2? So You hear rate of change, you know you're just looking for the derivative. So there's your formula, and we already know the derivatives for f prime, or excuse me, f and g at 2. So just math, and you end up with first derivative of p at 2 equal to 25. Just throw that on the old graph there. The question, is it increasing, decreasing, or neither? Well, it's increasing at a rate of 25 units on the y-axis per unit on the x-axis. So part D of the first question asks us to estimate the value of p at 2.03 using the local linearization of p prime at 2. So I'm just going to go ahead and calculate out the slope. A little bit of math. Okay, so then I've got it. So that's the equation for the line, and then I'm going to substitute in 2.03, math, and there it is. So at p is equal to 2.03, or when we plug 2.03 into our function p, we get, or I get, negative 33.25, which should be very close to what the actual p at 2.03 is. Of course, we don't have the underlying function, so we can't say if it's a little bit up or a little bit down, because I don't know if the function itself is concave up or concave down at this point. So just to invite some discussion in class, I guess I'd ask the rest of you if you think there's any way to figure it out with the information that we have, or if it's not possible to determine exactly, do you think there's a way to make a good guess, or hedge your bets? And if so, how confident could we be with that guess? So just throwing that out there. As a person who doesn't know a lot about math, maybe it's possible, maybe it isn't. So gauntlet thrown. Okay, part 2, trig, exponent, and power functions. So there are 3 more rules I want to take a quick look at because they're going to help us answer all the questions about the function in part 2. First up is the sine cosine derivative rule that says if you want the derivative of sine x, well, you just compute the cosine x. And if you want the derivative of cosine x, then you just compute the negative of sine x. I have a lot to say about this rule, but the short version is that I did not take trigonometry or geometry, or not to put too fine a point on it, algebra 2. So the work that I had to put into understanding this rule in the past 2 weeks just about cost me my last non-gray hairs, but now I know what a radian is. Next, we've got the exponent rule, which lets you find the derivative of a function that is an exponent of another number. I still don't know what a logarithm is, but I accept that this is a rule. And finally, we've got the power rule, which just says that when your input is being raised to a value, you can kind of downshift that value to get the derivative. With those 3 ideas in mind, let's look at the actual problem. We're given a function that represents the value of a person's investment portfolio in thousands of dollars in year t, where t equals years after January 1st, 2010. And let's let Desmos graph these ones because it's much better at it and it's so fast. The first thing we're asked to do with this is give the instantaneous rate of change for January 1st, 2012, aka set t equal to 2 and then figure out the derivative. So we'll just use that little sine rule and flip that into a cosine. We'll also do the logarithm, whatever that is, rule, and then we'll math, and numbers, until we get to a derivative there. So a derivative, so the v prime at 2 is equal to negative 0.6378. And what that means in real terms is that on that date, January 1st, 2012, this person's portfolio is losing value at a rate of $637 per year. We're going to talk about the second derivative in a moment, so I thought I'd just add the graph of the first derivative. Tangent line, get that in there. All right, so part B asks us to determine the value of the second derivative of our function at the same point. So all we need to do is take the first derivative and apply the same rules a second time. So we hit that logarithm thing again, and that cosine becomes a negative sign, and then we math, and second derivative. There you go. V second derivative 2 is equal to negative 5.33. And what exactly does that mean? Well, the first derivative tells us how quickly the value is changing. So if we could freeze that in place for a year, then the value would be $637 less than it is on January 1st, 2012. The second derivative tells us the rate of change of the rate of change. So in this case, it's saying that if we could freeze that rate of change, the second one, in place for a full year, then at the end of the year, instead of losing value at a rate of $637 per year, it would be losing value at a rate of almost $6,000 per year. Fortunately for this individual, we can see on the graph here that the second derivative has already reached its most negative value right there at that peak. And so it's going to, the derivative is going to decrease to 0, which I guess is another way of saying increase. So it'll increase to 0 around here, and then it'll pass 0 and keep going up until it reaches its maximum positive value down in this valley, and then it'll start to diminish back down. The last thing we're asked to do is take a look at the graphs of our functions and make some observations. So in the context of the problem, the graph of our function shows a value that it's got some ups and downs, but over time it's trending upwards, which is exactly what any stockbroker would try to tell you the stock market is going to do. When we graph the components of the function as separate graphs, we can see very clearly the two ideas at the heart of this function. The first component is just a logarithmic function that goes up and up and up with no end ever, while the other component uses a sine wave to build in some oscillation in the value. We add the derivatives of all three functions, we see that they all start to diminish. If we kept deriving derivatives, I suspect all three graphs would get closer and closer to each other. That's it for community problem number 2. I'll leave you with this cheery little reminder to not do what I did and procrastinate, not just in calculus, but in life. If you have any thoughts about the graph of the p function in part 1, let me know. And that is the end of my show. Thanks. Bye.